Hello and welcome to Standing Waves in Pipes Physics Video Waves.2a. Some of the animations we'll be using in here come from Dr. Russell's website, which we have used in the past. Here's the URL for that, for the animations we're going to use in this particular video, if you would like to check them out. Now, we have talked about waves on strings already, so in this video we will discuss waves in a pipe, which are very similar to those in a strings. However, one important difference is that on a string, it is the string itself that is vibrating, causing the waves, whereas in a pipe, it's the air column inside the pipe that is vibrating and causing the sound waves. And since we are discussing sound waves, we need to remember that we are talking about longitudinal waves and not transverse waves. Oftentimes we will represent these as transverse waves, but remember that sound waves are longitudinal. When we take a look at the simulation here, we'll notice that the top picture is of the particles themselves moving back and forth in the longitudinal fashion because of pressure changes that are occurring here on the left-hand side with the cylinder moving in and out. We also can look at this from the perspective of there being pressure changes as the cylinder moves in and out. The pressure at each instance and at each position in the pipe changes, going from a 0 to a maximum positive or negative value. And when we have the maximum positive value, that is when we have a compression. When we have the maximum negative value, that's when we have a rarefaction, when there's lots of space between the particles. We also can look at this middle picture, which is showing the longitudinal displacement of the particles from left to right. So we're looking at going up being to the left, going down being to the right. Let's take a look at the red dots here. Okay, there are 3 red dots in the top picture. We have one about the center of the pipe, we have one to the far right of the pipe, and we have one a little bit to the left. So let's start with the one in the middle of these 3. It is moving the most because it is located at what we call an antinode, place where it has a maximum displacement, where the pressure doesn't change. The one on the left is not moving at all. And that's because it is located at a node, at a point where the displacement is 0, but that's because there's a maximum change of pressure going on at that particular position. And the one on the right, on the far right here, is moving somewhere in between, because if we look at its position, it's not quite at a maximum and it's not quite at a minimum. It's not at a node and it's not at an antinode. It's somewhere in between. So it has some displacement as well as some changes in pressure. When we draw standing waves in a pipe, we typically show them like this center graph, because it is easier to talk about it that way, and it gives us a nice understanding of what's going on with the displacements at the ends of the pipe. Pipes that are opened at both ends, or tubes that are opened at both ends, are a lot of woodwind instruments. One in particular that I can think of that's not actually a woodwind, but is open pipes, are organs. A flute is open at both ends. Some organ pipes are open at both ends, and some are open at only one end. When we are talking about pipes that are open at both ends, they have pressure nodes and therefore displacement antinodes at the ends. So if we take a look at these 2 pictures here, on the left we show what it looks like according to the displacement of the air, and on the right we are looking at what the pressure variations in the air are. Notice that there have to be antinodes at the openings of all of these pipes when we're talking about the displacement of air, because there's nothing for the air to reflect back off of. So it's going to be an antinode. There's going to be maximum amounts of displacement there. And when we are looking at this picture on the left compared to the right, we'll notice that they're opposites. If we look at the right for a minute, we can see that we have half of a waveform in pressure variations in the length of this tube. Well, we have half a wavelength in the left-hand side in the displacement of air as well. It's just positioned a little bit differently so we don't see it that way. This first picture here is talking about what we call the first harmonic. The first harmonic is also called the fundamental frequency, and the fundamental frequency is the base frequency of the sound for this particular pipe. When we look at this, is what I just said before, the length of the pipe is equal to half of a wavelength, 1/2 lambda. And keeping in mind that we are talking about waves, so V is equal to F lambda. So if I solve this for the frequency, the fundamental or first harmonic frequency then is the speed of the wave divided by 2L. Why 2L? Because L is half a wavelength. This is the base tone that the organ would produce at this frequency, or at this length rather. And the next two pictures down are what we call the second and third harmonics. These tones are also produced depending on what the organ is doing and how much air is going through. You can have the fundamental as well as the second, third harmonics continuing on up. So the next pictures down, this next one is called the second harmonic. And in the second harmonic, L is equal to lambda. So if you look at this, the entire length of the tube is taken up by one full wavelength. And the frequency, again, using V is equal to F lambda, the frequency of the second harmonic is V over lambda. So in this case, it would be V over L. Well, take a look at that. V over L is just twice what the first frequency was. So the frequency of the second harmonic is twice the frequency of the first harmonic. So there's a relationship there not only between the lengths and the lambdas, but also between the frequencies from the fundamental or first harmonic to the second harmonic. Now when we move to the third harmonic, you can notice again that our number of wavelengths have increased again in the same amount of space. So for the third harmonic here, the length of the tube is now not going to have half a wavelength or even one wavelength. It's going to have 1.5 wavelengths. So it's going to be 3/2 of the third harmonic's wavelength. So you see we've got half, and then we've got 1, and now we've got 1.5 wavelengths in there. So the frequency of the third harmonic is going to be 3V over 2L, which if we look again going back up, well, V over 2L is the fundamental frequency. So 3V over 2L is just simply 3 times the fundamental frequency. So the first harmonic's frequency is V over 2L. The second harmonic's frequency is V over L, or twice the first. The third one is 3 times the first. It continues on like this for as many harmonics as can fit within this pipe. So when you have open-ended pipes, all whole number multiples of the fundamental frequency are possible. So you could have, this could continue down. So you could have F7, the seventh harmonic, would have a frequency of 7 times the fundamental frequency. And it would just keep going on and on and on and on. And when you're talking about a flute or an organ, when you're playing a note, that means that all of these overtones or all of these harmonics are possible to be produced. You have to have perfect fundamental pitch in order for them to be produced. So they aren't always seen in real life, but they are possible to have there. Now let's see what happens if we plug up one end of the pipe. Now, if we plug up one end of the pipe, we could still be looking at an organ pipe, just not all of them. We could also be looking at a clarinet. And in this case, you can see that they're very similar to the open pipes, but there's some key important differences. Now, if you look at the first one, we don't have a half wavelength. We only have a quarter wavelength. So the length of the pipe can only create a quarter wavelength of a wave if we have one closed end. So if you can only create a quarter of a wavelength within that pipe of length L, that means your fundamental frequency is not going to be V over 2L as it was before, but it's going to be V over 4L. So when you go to the next harmonic, you cannot end up with a harmonic that has a node at the end. The next harmonic that can occur or overtone that can occur is not until you have 3/4 of a wavelength. So L for the third harmonic, there is no second harmonic because that would require a half a wavelength, which we can't have. So we have a third harmonic where L is 3/4 lambda 3. And F3 is 3V over 4L, which is 3F1. So that relationship is still the same, that F3 is 3 times the fundamental frequency, just like it was with open pipes. And again, we can't have a situation where we have a fourth harmonic, because the fourth harmonic would require that you have a node at the opened end, and we can't have that node. So we skip the fourth harmonic, and we move on to the fifth harmonic. So the length of the pipe is 5/4 lambda 5, and the fifth harmonic frequency is 5 times the fundamental frequency. So same sort of relationship between frequencies with open pipes as with closed pipes. However, the important thing here is that when you have a closed pipe, you only produce odd harmonics. This is very important to remember because this changes how sound is acting within the pipe. It also changes the sounds we get and what we hear and what we can actually make with an instrument that is a closed pipe. So if we have closed pipe instruments that can only produce the odd harmonics, like a clarinet, we have other open piped instruments like a flute, which can produce all harmonics, even and odd. What does that mean in terms of what we hear and what we listen to? Well, if you think about it for a minute, the amount of overtones that you get is really what contributes to the quality, the tone, the timbre, the color, the feel of the instrument and the sound that comes from the instruments. So when we look at wind instruments, let's say for a moment that we are going to compare a clarinet, a piano, and a violin. And they're all playing the same fundamental frequency. So I'm going to tell them all to play, say, a middle C. And when they play that middle C, theoretically speaking, they should all be playing the same frequency if it's middle C, and therefore it should sound the same. But we know that that's not true. And the reason that that's not true is partly because the material the instrument is made of is going to have an effect on the sound. Another thing is that the overtones that are produced within the instrument are going to have an effect on what sounds you hear as well. Now, of course, I'm about to show you some graphs on what the overtones look like with these three instruments. So we have clarinet, piano, and violin, the relative amplitudes of their tones and their overtones. You can see here that the fundamental frequency is always the lowest frequency on the list, and then the harmonics are the ones that go up. Now, if you look at the clarinet, to begin with, these harmonics are not all of the harmonics. We are not producing all of them. It's not until we get pretty high up here that we start to produce all of the harmonics. On the piano, we are producing all of the harmonics, but to different degrees until we get up here where we skip some. And again, this is because this is real life. This is not, oh, this is how everything works, physics. This is talking about what it really looks like in real life. Now, the violin, of course, is a string, which is essentially the same as having a pipe that's closed on both ends, so you have to have nodes on both ends. You can see that it produces a completely different set of harmonics than either the piano or the clarinet, which is why even if we have them all playing the same note, the same fundamental frequency, they're going to sound very different because all of their overtones are going to be different. Now, one of the really interesting things about overtones is that you can have a clarinet playing, for example, and you can hear it as a full wave. Now, ideally, if it's just playing the fundamental frequency, you will hear a perfect wave. And as we said, it would be a quarter of a wave, but it's got all these overtones playing. So not only would this be occurring, but you might also have this occurring at the same time. And you might have this overtone occurring. Whoops, sorry about that. So you have all of these different tones occurring together. Well, we know from talking about waves and the addition of waves and superpositioning of waves before that this is going to result in some crazy looking wave that's going to go, like this all over the place. And it's not going to look anything like the really pretty little quarter wave pattern that we have, or the 1.5, or anything like that. How do we figure out all of these overtones? How was this graph created? Well, what they do is they do something called a Fourier analysis on sound waves. And essentially, a Fourier analysis is looking for the ideals. It's looking for all of the overtones that are possible. So it takes this crazy put together combination, superpositioned waveform, and it takes it apart based on if it has a fundamental frequency, there should be a quarter wavelength. There should be a 1.5 wavelength, etc., etc., etc. So a Fourier analysis allows you to take a crazy waveform, and knowing about the fundamental frequency and all the harmonics allows you to separate it out, so we can create graphs like this that show us the relative amplitudes and which harmonics, which frequencies are actually being produced. Okay, so in this simulation, we're going to start with a pipe that has 2 open ends. And we have just the first harmonic showing here. You can see how the particles in the center aren't moving, and those at the end have the largest displacement, just like we had before. The frequency is 0.067 hertz. The period is 15 seconds. The wave speed is 100 centimeters per second. Wavelength is 1500 centimeters. So if the wavelength is 1500 centimeters, then this tube must be pretty long as well, right? Half of that. All right, we're going to add a harmonic. So now we have the second harmonic going here. And notice that we have 2 points that don't move off of the center line. If we add the third harmonic, we have 3 points. The fourth harmonic has 4 points. And again, the blue and the orange waves inside are looking at all of the particles. So some of them are going to be going in the positive while others are going in the negative at the same time. So that's why we have 2 different waves here. So this is the fifth harmonic, sixth, seventh, eighth. Whoa, that's really going crazy there. Now, if we suddenly change this to having only one open end, remember the length of the tube is only a quarter of the wavelength. So this is the first harmonic. The second harmonic is going to be 1.25, so 3/2. Sorry, it's going to be 1.5, so 3/2 wavelength. Then 1.25, and it keeps going. Fifth harmonic, sixth, seventh. Notice that the end near the open end of the tube, there's always motion there. So if we keep adding harmonics, it's going to keep increasing the wavelengths. Sorry, it's going to keep decreasing the wavelengths and increasing the number of waves within the pipe itself. At this point, you can see that a whole heck of a lot of harmonics could fit within this pipe, even though it's not an infinitely long pipe, and it should, in fact, you would think that it would have a limit to it. Okay, so this gives you a good introduction to harmonic waves in a pipe, whether they are one end closed or both open, and how wind instruments fit into this. Next video up, we will do some problems and some calculations to make sure that you know how, in fact, to solve problems dealing with these pipes. So bye for now.